Okay, guys, so let's continue our lecture on beams laterally supported. So let's now try to understand the concept of plastic hinging or plastic hinges. So this has something to do with uh, these factors here that once all of the fibers have yielded, we note that your section will lose some or maybe all of its resistance to rotation. Of course, I say some because normally in actual design, we do not expose 100% of such plastic rotation to occur. And this lost maybe one way, shall I say, a disadvantage. Okay, so if you look it on one way, but on other side, always look at the coin, no? Dalawa yung side niyan. When you say lost, parang disadvantage siya. Pero on the other side of it, there is some uh, property that is being boosted, and that is ductility. Okay, you see when there is a loss, no, in the resistance to rotation, it's tantamount to saying that you have absorbed some form of energy into it, such that if the load applied is cyclic and at the same time transient. Okay, ano yung cyclic na load na transient? Yung cyclic, yung pwedeng umulit pero mawawala rin. Mahirap kasi kung cyclic pero hindi na siya sustained na siya, ay delikado yun. Ano yun? Yung earthquake, di ba? So, when earthquake hits a structure, mas maganda na magkaroon ka ng loss the resistance sa rotation because you are actually dissipating a small amount of energy tantamount to saying that your the ductility property has been achieved by the formation of these plastic hinges. Okay? So in this particular behavior, the section behaves like a hinge, just like an external hinge, no? Ang kaibahan lang is that meron siyang constant resistance uh, which is there for as long as the integrity of the point in which the plastic hinge occur is not deteriorated. So, kaya kumisan pag alam mo dun magpa-plastic hinge, anong ginagawa mo? Naglalagay ka ng mga stiffeners, okay, para nun, yung integrity niya, ma-maintain mo. Okay, sa concrete, anong ginagawa mo? Confinement, no? Sa steel naman, stiffeners. Okay? So sa on our third note, after such, okay, behavior has been achieved, we say that the section has formed at a particular location what you call a plastic hinge. So internal ito, no? Internal siya dun sa mismong sectional property. Pero yung behavior niya, para lang siyang external hinge, no? Okay? So this concept is the basis of what you call the limit design or the plastic design or simply the performance-based design in which your pushover analysis is has been popularized by so many structural enthusiasts. So if I have here now a simply supported beam into its simplest form, this is a structure, and I have here an elastic moment equivalent to WL squared over 8. What will happen to the beam if I allow it, okay, to reach a plastic behavior by forming or by allowing it to form a plastic hinge here at the midspan. Can we allow the beam to form a plastic hinge somewhere else? Okay, so yun yung mga question na normally, pag ako ang nagbabasa, yun ang mga una kong pinag-aaralan, no? Uh, Huwag kang mag-stick lang dun sa sinasabi, dapat magtanong ka. Ang mahirap kung walang sasagot sa iyo, yun ang mahirap, ano? O kaya may sasagot sa iyo pero hindi rin alam nung pinagtanungan mo, mahirap talaga. Okay? Okay, anyway, we'll deal with that later, assuming or granting that the plastic hinge occurs at the middle, and this is now the normal condition, no? Bakit sa middle? Kasi ito yung unang mama-maximize, no? Assuming your beam is prismatic. Okay? I have a prismatic beam here. So the word prismatic is very important. Why? Because we are now defining the property of the material to be at least based on this property of being prismatic. When you say prismatic, the section all throughout has the same property. Okay, yung sa elementary definition natin ng prismatic, shape lang ang sinasabi sa atin, no? But in my own opinion, prismatic property is in general the overall property, not only the shape of the section, but also the property of the material inside that section. I'm talking here specifically of reinforced concrete. Di ba yung section mo rectangular pero hindi prismatic yung reinforced concrete kasi yung bakal mo dun hindi naman pare-pareho yung sections mo, no? Okay, so that's just one of the many situations wherein being prismatic does not mean being of constant cross section. Okay, so here is now your beam allowed to what? Ito yung sinasabi ko sa iyo na yung plastic analysis class can be accounted for by factoring the service load. Kita niya, no? Factoring. Although this is not basically giving you the actual plastic analysis per se, but it can actually approximate the increase in the service loads to the inelastic or plastic load by way of applying the factors, the overload factors. Okay? Okay, so nag-hinge siya dito. By the way, how many hinges do I need? No? Ang unang tanong mo, when you're analyzing a plastic frame or a plastic beam, how many hinges do I need? Or plastic hinges? Okay? So, ilan yung plastic hinge na kailangan ko dito? So, ito na yung sagot, di ba? Isa. Bakit isa? Okay, so let's talk now of what you call the degree of indeterminacy. Can you still remember what the degree of indeterminacy is? So for this particular beam, what is my degree of indeterminacy? Okay, so we will review that later. Okay, we will review that later for those who have some doubts. No, but the correct answer is 0. Okay, so the number of plastic hinge is simply DOI plus 1. Okay, so that's the formula. So I need one plastic hinge to fail this mechanism, this system, this uh, frame. Okay? So isa lang ang kailangan ko to fail it. And this is very critical, no? Delikado ito kasi once na nag-overload ka, isa lang patay. Patay si beam, di ba? So, kaya lang, example lang ito class, no? Pero I suggest do not do a design wherein you only need one plastic hinge, no? Okay, so this is your elastic, this is now your plastic moment diagram wherein the value of your uh, your maximum moment is simply the superposition of the factored service load WU, which answers the question kanina ni Engineer Ladringan about how do you easily address. Okay, so pero ito ngayon ang prove natin. Ano ngayon yung WU such that this will behave in a real plastic behavior. Okay, so note that the plastic moment MP may be obtained by two methods. Ito yung pinakasikat naman sa plastic design, no? Or plastic analysis, yung equilibrium method or other energy methods. Specifically, I'm very fond of using the virtual work. It's the easiest energy method that I know. Castellanos theorem, if you heard those theorems, ano pa, ang dami niyan, di ba? So, pero yung virtual work, napaka simpleng gamitin, madaling intindihin. Okay? So, virtual, ano pa siya, no? Naka-trend pa ngayon kasi virtual yung mga, ano natin ngayon, di ba? Mga events natin ngayon. Okay? So, virtual work. So, the difference between the real hinge and the plastic hinge is that the latter offers a constant resistance MP against rotation, just what I've told you. And the number of plastic hinge to form a collapse mechanism is 1 degree higher than the degree of static indeterminacy of the system. So, tandaan nyo lang yun. Pag alam nyo yung DOI, static indeterminacy ito, no? Kasi meron ding indeterminacy na internal, eh, no? Ito, kumbaga ito yung tinatawag na external indeterminacy. Okay, when you say,
po, na sir?
yes, we are talking more on these boundary conditions. Global, in short, we are talking of the global failure mechanism, not the local failure mechanism. Because sometimes stability is not just global, but it's local. No? So, tignan nyo, related na lahat yung mga pinag-uusapan natin on what is global, what is local. Di ba? So, umiikot lang yung structural engineering sa mga ulit-ulit na concept. Iniiba mo na lang, particularly kung ano yung ginagawa mo. No? Siyempre, nag-iiba siya kung iba yung concern. Okay? Okay, so this is now siguro ito na yung pinaka-solution niya, no? Before we solve it by virtual work, ito yung moment rotation characteristics niya at kailangan mo to sa pushover analysis. Parang yung ginawa natin moment curvature sa RC. Okay? So, importante. Ganun din ito, no? Di ba ganito rin yung shape ng moment curvature? Okay? Ayan yung yield curvature mo. Ayan yung curvature mo at a certain point. Okay? Ito yung ultimate curvature mo. Ano yung ultimate curvature mo? Pag nakuha mo na yung pinaka-ultimate strain mo, definitely, merong definition yan. Yung code-guided. Like sa concrete, that is sa concrete, the ultimate strain is different based on the code. No, it's 0.003 in ACI and I think 0.004 or 5 in British, in Canadian codes, iba, in Indian codes, iba. Okay. So dito, meron ka ring uh, uh, ultimate curvature based on ultimate strain. Ito naman yung ultimate curvature mo. When I say of curvature and rotation, they are just the same. Tama? Rotation means ikot, no? Curvature means curve. And when we have a beam that has curved or that has bended, then there is rotation. So they mean the same thing, but they are not exactly the same, of course, because rotation is unitless, dimensionless, while curvature has a unit. Anong unit ng curvature? Ha? So if
Dimension.
you, ah, ano yung unit ng curvature? Okay, so phi is m over ei, tama? So tandaan niyo yung mga notations na yan, no? What's moment? Moment is kilonewton meter. This is what? This is Newton, kilonewton per, or say meter square. Okay, kilopascal, and then this is millimeter to the fourth. Tama ba ako? Okay, so this you cancel, 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 cancel. What will be your unit? It's 1 over meter. Or, if you are very small values, this is millimeter. So the curvature is a per millimeter thing, okay, per millimeter. So if I multiply this by the length of hinge, let's say length of plastic hinge, pH, ano ba length? Length is in millimeters. Okay, so if I have a beam here and I want to put a hinge here, I put a stiffener there and some maybe extra uh, plates, no, to make sure that this will not or this will be able to withstand or maintain a rotation MP. Okay, so what's the length of this? L. So if I multiply phi times L, my unit is now your rotation, theta. Okay? Millimeter over millimeter, so this is now in radians. Okay, radians is a dimensionless unit. Take note of that. So if I expect some plastic behavior that's happening here, of course it's another topic to let you know how to design such a plastic hinge location. Okay. Okay, so this is now our graph, and we go back to the method of virtual work on how to solve WU. Our target is to solve for WU. And take note that virtual work is only about summing up the work or energy must be zero. Or you separate the internal with the external and equate it. Tama? Okay, so this is now the external work. The external work must be done by the external force, WU. And the internal work must be done by the internal force, which is the moment. Okay? Okay, so these are generalized forces. Okay? Work is simply force times distance. Okay? Force times distance. But this is an external load. This is an internal load. So when we talk of distance, in terms of moment, this is rotation, okay, theta. And this is simply deflection, delta, okay? Okay, so force. Where's your force? Your force is simply your weight, no? WU times L over 2. So why is it L over 2? Because I subdivided the fact that I have two segments, okay? This is my load, okay? So this is my support here. I have two segments. I simply multiplied the total force here by WU times L over 2. Okay? So this is my force. And the distance, if this is my delta total, at the centroid of this, I have a delta over 2. Okay? It's my distance. You concentrate, of course, your load at the centroid of the load distribution, and that is at this point. Okay, so this is now 2. Why? Because you have the other side of the segment. And equating it on the moment, where's the moment? So internal moment is only happening here. Okay? The internal moment is only happening here. Of course, the plastic hinge is assumed to be a point. And if I now make a deformation, rotational deformation, uh, in terms of the uh, original segment of your beam to its deformed segment, this is what? This is simply my total rotation alpha. Okay, and if I define a certain angle here, let's say theta, and another, of course, I assume this is a uniformly distributed symmetrically shaped, this is also theta, I can say that this is 2 theta. So I place a P there to simply indicate that I'm now doing a plastic analysis. We are now talking of plastic rotations. So this becomes 2 theta P. And solving theta P by geometry, so since this is simply delta over L over 2, and this is 2 delta over L. Okay, so it's not difficult to look into the system. And substituting, we get now your WU simply equivalent to 8 MP over L squared. So your plastic moment is simply equal to WUL squared over 8, which is actually the same as your service load moment equation, which is, di ba, sa service load, your M maximum is simply WL squared over 8. Okay, so this is the reason why a simply supported beam is not a good system to talk about when it comes to what? When it comes to achieving, okay, the plastic behavior, because your WU is simply the same formula, or sorry, your moment is of simply the same formula you can have on your elastic moment equation. So you better do some good system design, and that means additional degree of indeterminacy to come up with a very efficient system to exhibit a plastic behavior. So yun yung kumbaga moral lesson doon, no? Do not do a plastic design on a simply supported beam. Aside from it's dangerous, it simply gives you the same degree or level of magnitude when it comes to the comparison between the plastic moment and the maximum moment. Okay, so for the moment curvature relationship, we try to look at the elastic and plastic stages now here to come up with some formula eventually on the plastic moments, and graph the moment versus uh, alpha relationship. So, dito, gumamit naman ng ibang variable instead of a moment versus, tatlo yan, eh, no? Moment versus theta, a moment versus curvature, and a moment versus alpha. So, sa mga software, I don't see an alpha because alpha is simply, can simply be derived by phi here, no? Parehas lang siya. Ito lang yung madalas na makikita mo sa software natin, no? So how do we derive the curvature relationship? So take note that in the elastic, your m is equal to ei phi, which is up to a limit of my sx fy, where phi is equal to your yield curvature equivalent simply with your epsilon and distance from the neutral axis. Okay, so of course we're talking here of a beam. Okay, so if I have a rectangular beam, my phi value is simply your epsilon that describes your yield divided by your h over d. So this is for rectangular section. But for an elastic or elastoplastic stage, this may happen. No? So we have actually a scenario in between a fully plastic and a partially plastic strain and stress distribution. So for the strain distribution, your epsilon y may be exceeded by a factor alpha, which correlates with a stress distribution equivalent to this trapezoidal distribution. Okay, so if I assume a distance xo coming from the neutral axis, that defines the point into which your elastoplastic stage is bounded, no? At this point, then from this figure, we can derive the moment curvature relationship. And how do we do this? So we do this on the basis of equilibrium condition. First, we define what is alpha. Alpha ey all over h2 is just by Ratian proportion is equal to epsilon y all over xo. Okay, canceling epsilon y, we define your xo to be h over 2 over alpha. Okay, so alpha is simply a parameter that describes this boundary here, okay? The point into which your elastic and the plastic stage is bounded. Okay, so this is a transition point. So for the moment, we simply solve for the internal, okay, moment by simply looking at the centroid here, and then the centroid here, and then simply make use of the couple. No? So you have here the couple. This is the moment arm, D. Okay. Let's not use the O there. It might be confusing to use O. So let's just call it D. Or we can divide this into two, for easy computation, into two areas, the triangular and the rectangular area. So if I now multiply Fy times B, okay, the width of the rectangle is B, and this is now my vertical distance, H2, I'm referring first to this rectangle, so this refers to the rectangular, okay, part. So H over 2 minus XO times the moment arm is what? The centroid up to the neutral axis. Okay, so this is just an average value, you know. So I just take the average of these two distances to get the moment arm. Or you can divide this h over 2 minus x over 2 plus xo. So you get now this one here. So this is my d1, okay? And then times 1 half. Kasama pala to. Kasama siya. Ayan. Multiplied by 2. Bakit 2? Kasi dalawa siya nandito sa baba yung isa. Plus, itong triangle mo ngayon is 1 half fyb. Okay, the force multiplied, the stress times the width. Kaya lang rectangle siya, kaya may 1 half. Okay, so this is xo, this height, multiplied by the moment arm. So this is totally your area for your triangular section. And this is the d2. Okay, it's 2/3 of xo. Okay, some manipulations will yield to this equation. And substituting the value of xo in terms of alpha given by this definition here, you can get this here. Okay. Okay, so how do you verify this? Let's check. Baka meron tayong error dito. Okay, so xo is h over 2 alpha. So I can now substitute h over 2. Okay. Tama? Okay, so this is now squared. Eh, may natirang 3 doon, 1/3. Okay, ano mangyayari dyan? So, this becomes 1/3 times 4. This is 6. 12. Okay, kaya naging 12 yan. No? 3 times 4 is 12. Alpha is squared kasi naka-squared. H was brought out, squared. Ayan, nilabas yung H. May H doon. So, 1/4, tama siya. No? So, this is correct. So, I'm just trying to verify kung minsan may typo error siya. Okay. And you can also make use of this formula. What's the difference between this formula? This is in terms of your yield relationship. Okay, so my is actually your yield relationship equivalent to fy. What's the formula for fy is m for a rectangular formula. So this is simply m 6 over bh squared. Okay, so ganyan siya, di ba? So if this is y, my my is simply equal to fybh squared over 6. Okay, so dapat ito, target mo doon para makuha mo yung 1 minus 3 alpha squared. So labas natin ito. So let's look into it. 1/4, 1 over 12. Labas natin yung 4. Anong matitira? 1 minus 1/3. Tama? Ayun. 1 minus 1/3. So pag nilabas ko yung 1/4, may 1/4 dito niyan. No? So may 1/4 fy alpha squared. Okay? bh squared. So may 1/4 siya. Ayan. Eh bakit 6 ito dito? Okay, so here's the explanation, class. Okay, note alpha 2 over 3 times 2/3 is the coefficient of my, the value in the parentheses. Ayan, 4 siya dito. So, yun ang nangyari. Okay? So, if I substitute alpha is equal to 2/3, I will now have, okay, so I will have a moment equivalent to, okay, pag naglagay ako ng 2/3 dito, Fy, magiging BH square over 4. Cancel 6. Ayun. Okay, so yun lang yan. So our insert here is that alpha is equal to not alpha, but okay, 2/3 at m equals m. Okay, so that is now your definition of alpha, which defines the point into which, ayan, the point into which your my and mp ratio is equal to 1. So how are we going to prove this? So I made a program because I wasn't convinced that time about the Salmon Johnson. I made a program to plot the curvature relationship using MathCAD. Talagang ito na lang yung ano ko pinakamabilis ko na tool, no? Sometimes you don't understand looking at the equations, class. You might as well do a program to appreciate it in terms of the graph. So here's how the program works. No? So I define a range of values for alpha. And again, alpha is simply a function of xo. Ayan ha. Ito lang yung alpha ko. No? Alpha is h over 2 times xo. So it's a dimensionless parameter which can be related to phi later. Okay? So, curvature. Tuturo ko rin sa inyo kung actually, I don't know if nasa Salmon ito, no? I think I have found this definition in other references. I just grab it. But please check it, no? I'm not sure, no? Although the program is an original program by me, no? So I claim this representation of your moment versus alpha. Hindi ko lang natuloy na research ito kasi noon gusto kong mag-research sa plastic kaya lang nahinto siya eh. Okay, so the alpha is ranging from 0 to 10 maybe, and then note that alpha is not the curvature. Assume a dimensionless moment ratio. Dimensionless na nag-graph ka kasi mas magandang dimensionless. Hindi mo na kailangan ng actual moments. You only get the ratio. Okay, so if alpha is less than 1, ano ibig sabihin? Pag maliit yung alpha mo, I'm in the elastic part. Tama? Alpha is less than alpha ey is less than ey, then I'm on the elastic stage. Dapat straight line ako. Tignan nyo dito. When alpha is less than 1 or exactly equal to 1, straight line ako, elastic. Okay, so kaya ako ginawa ito nun dahil meron akong pinupush over na steel nun eh. Mahilig pa ako nun sa kahit na pinag-aaralan ko pa eh. Ngayon, kalimutan ko na rin kung paano ginawa. And STAAD pa gamit ko nun, class, because STAAD that time can only do pushover in steel. It cannot do it in RC. That's why I was forced to use it SAP 2000 because SAP 2000 can do RC pushover, no? Ewan ko lang ngayon kung kaya ng STAAD. Matagal na akong di nag-update ng software. So, nakita niyo ito, no? When alpha is less than 1, ang maximum ko is alpha times 2/3. Ayan. Straight line siya. When alpha exceeds 1, ay ito na siya. No? Ito yung kailangan mo sa curvature relationship. Ito yung kinukuha ko. No? So, pag prinat ko to sa SAP 2000, dinefine ko sa FEMA guideline, ito na yung gagawin. Ini-straight ko na ito. Normally, ako ang ginagawa ko, ini-straight ko siya. Para sure. Ayan yung aking plastic hinge definition. Of course, ano yan ha? Hysteretic yan, ano? Pag nag-earthquake. Okay? So, meron kabila yan dito, ano? Yan. This is my point A, I think, and my point B, C, D. Okay, this is my immediate occupancy, collapse prevention, and life safety. Balik to data. Immediate occupancy, life safety, and collapse prevention. Okay, so IO, LS, CP. Ayan. So, kung hindi pa kayo hindi nyo masyado alam ito yung pwede i-share sa inyo pag nag-aral na kayo ng pushover. Okay, so ako ginaganyan ko yan. Ayan. So, ito na yon. Kung minsan, nilalagay ko na dyan. Pag tinatamad ako, finifix ko na yung value straight dito. Okay, so, may automatic kasi class, no, sa SAP. Kaya lang, sabi ko nga sa inyo, delikadong gumamit ng automatic na weapon, ano? Kasi hindi mo alam ano mangyayari. Mas maganda alam mo talaga yung ginagawa mo. Kaya kailangan naintindihan niyo itong mga curvature. I'm not using alpha actually kasi wala pa yan sa software. Pero dito ginamit ko lang alpha. Okay? So this is my plot. Very easy to follow if you want to do it in MathCAD. Okay, so that ends my second lecture video on this. If you have questions, let's talk it outside this video. Thank you very much.